second.
Hello everyone, my name is Yuanlin Gu. I'm currently a postdoctoral research associate at Computer Science Department of Loughborough University. Today I'm going to present our paper named Improved Cloud-NARX Estimation Algorithm for Uncertain Analysis of Air Pollution Predictions. So first, I would like to introduce some basic information of this work. So this work is funded by Innovative UK and Newton Fund. And for this project, we have 4 partners from both United Kingdom and China. So for the UK side, Loughborough University is a partner from Higher Education, and Satoshi Systems is a company based in London from industrial side. In China, we also have 2 partners, which is Shenzhen Institute of the Advanced Technology and EEG Smart. So in today's presentation, I will talk about the aim and background of this project, and I'm going to introduce our proposed method, and I'm going to talk about data description and data visualizations. I'm going to show you the experimental result of using the data and our method, and finally, I will give a summary of this work. So a little bit aim and background. So air pollution is a long-term cumulative challenge faced by the whole world. Especially, it is crucial in many developing countries. And as we all know, air pollution can cause many significant negative impact on both climate, environment, and human health. And this makes the monitoring and forecasting of the air pollution index crucial. For example, popular index is PM 2.5. So many machine learning methods have been employed for the PM 2.5 predictions. These methods including the neural network, regression, Bayesian, or enzyme models. But these models mostly focus on improving the predictions of the PM 2.5. But one problem is that there are always some strong uncertainties in the predictions, especially in peak values. This can potentially increase the prediction error and decrease the prediction reliability. So it is crucial to evaluate these prediction uncertainties. A popular method is to produce prediction intervals from the models that can quantify the uncertainties of these predictions. So the prediction intervals can provide the information of the confidence band in the predictions. For example, you can see that in the red figure, the red line is the predicted values, traditional predicted values, and the blue line indicates the true values, the observation values. This is what the traditional machine learning models can do, but for the quantification of the uncertainties, we need the prediction intervals, which are highlighted in green shadow. It indicates the possible true value, a range of possible true values in our predictions, so we can know that what are the risks using this kind of predictions. Our proposed method is based on the Cloud-NARX model. So I want to introduce a little bit about these Cloud-NARX models. So you can see that in these equations, it is actually a polynomial models where the phi here is the model terms, which we also call the predictors. But the difference is that it did not use the traditional point estimation as the weights. Instead, it employs a model called cloud models as a fuzzy representation of the estimated weights. So it's not only a point estimation, but the quantification of distributions of the estimated parameters. So it can quantify the uncertainties in the estimated weights, and therefore it can go forward and quantify the uncertainty in predictions. So, looking at the figure below, we can see that the cloud models is a fuzzy representation using 3 parameters, EX, EN, and HE, which I will introduce in the later slides. It can be estimated from a series of drops, which we can also consider them as element of a distribution. So this is the basic information of these Cloud-NARX models. And in next slide, I would like to explain more details of some of the concepts. So the first thing I want to explain is the model terms, which are indicated in by these equations. So the model terms are predictors, but not only the original variables from an input, it can also be the derived and selected variables to describe the system dynamics. For example, for a dynamic time variant system, we can add time lags to analyze the discrepancies of the output variables on the input variables that is collected in history. And we can also add nonlinear terms to help the model to better describe the nonlinear dynamics of complex systems. But these model terms can have a huge number. So not all these generated model terms are useful. Some of them are not useful in a structure model. And in addition, if we use all the terms into a model, there can be some overfitting issues. So we pick out the most important terms from the series of candidate terms using an algorithm, a feature selection algorithm called orthogonal forward regression algorithms. I won't introduce many details of this algorithm, so I just want to mention that it's an algorithm used for the feature selection. The next concept I want to explain a little more is cloud models, which I indicate as C in these equations. So the cloud models are used to replace the classic point estimated parameters, which we also call weights, to describe the distributions of the parameters and measure the uncertainties. It employs three parameters, which is EX. It means the expectation of the distributions. The EN, which means the variance of the distribution. HE is hyperparameters, which measures the degree of distribution depart from Gaussian distributions. So in general, you can consider EX and EN as the mean and variance of Gaussian distributions, but actual HE parameters can measure the distributions more accurately than the Gaussian distributions. You can see that in the right-hand figure, we have an example of the cloud distributions. It has a similar shape of the Gaussian distributions, but you can see that it contains more details rather than the Gaussian distributions. So the next, I want to introduce the proposed algorithms of this work. So for the classic Cloud-NARX model, it comes with a traditional estimation algorithm, which we name as conventional CSNE algorithms. So in the traditional algorithms, you can see in the right-hand figures, it contains some basic steps. So for the original time series data, it resample with the rate to form k sub-data sets, and then it uses feature selection to select the important terms and structure models for each data set. And next day, the cloud models can be estimated to describe the estimated weights. And next, the Cloud-NARX model can be estimated using these cloud models and model terms. This model can be used to generate PIs, but here is all the procedures in the CSNE algorithms. So if we generate PIs is not good, it's not accurate, we need to choose another resample rate and start from the beginning to generate another Cloud-NARX model. This takes a lot of time and it needs many manual operations and experiment. So our work proposed a new method by adding a recursive estimation procedure and also two criteria to evaluate the PIs. So we can evaluate the PIs automatically after this step, and if the PIA and PIW, the two new generated criteria, is satisfied, we can say that our optimal model is found. But if it is not satisfied, we can move to the resample rate update formula, and then we use this formula to update the resample rate automatically and replace the procedures until an optimal model can be found. So no human operations are needed in these algorithms. It largely reduced the amount of time for training the model, and it also have better accuracies on building an optimal Cloud-NARX model. So here are the basic ideas of our proposed method, and I would like to introduce a little more about the two new criteria. So the first criteria is called the prediction interval accuracy. It measures the proportions of the true observation values which are within the produced PIs. The second criteria is called prediction interval wise. It measures the difference between the lower and upper boundary of the prediction intervals, and you can also say it measures the width of the prediction intervals. So normally, in general, the high PIA values and the low PIW values indicate that the prediction intervals is accurate. So for the criteria of whether the PIA and the PIW meet the threshold, we choose a predefined threshold both for PIA and PIW. So for example, in this study, we choose the threshold of PIW to be 0.3 to guarantee that the width is not too large. So they can provide meaningful information or predictions. For PIA, we need to choose different values depending on the data. So because in this study we have two data sets, so two different PIA thresholds are chosen for the two data sets. So if both the two conditions are satisfied, that means that the estimated models have good accuracy. But if it's not satisfied, we want to update the resample rate and repeat the estimation process until we get a good model. So our proposed formula for updated resample rate is shown in the equations. So you can see that this is the target resample rate we want to update, and this is a resample rate of these previous types, and we have update factors to update the resample rate. So these are the basic ideas of method. Now let's move on to the experiment results. So we use air pollution as a topic. So our aim is to predict the PM 2.5 index from some weather data. You can see that we have weather data including, for example, sunlight, humidity, temperature, wind speed, rain, and also season and wind directions. For the raw data set, we have pre-processed the data. For example, we remove the outliers, which means that it's extremely high values caused by the measurement error, and we fill the mean values. We also dummy code the category variables, which, for example, seasons and wind directions. After pre-processing, we have a range of continuous time series, which you can see that there are no missing values and outliers in the time series. So this can be directly used in the systems. In this slide, I would like to introduce our identified models. As we mentioned, we use some feature selection to pick the most important features from the candidate features. So in this case, we pick out a number of 6 features. For example, the first one is the PM 2.5 1 hours ago. And for example, the third one is the conduct of northwest wind 1 hour ago and PM 2.5 2 hours ago. So these selected terms are interpretable, so you can clearly say what are the factors are affecting the PM 2.5, affecting the predictions. These terms are connected linearly by their estimated cloud models and their and other terms. So for each model term, we have 3 parameters to describe as a Cloud-NARX model, cloud models, which is EX, EN, and HE. To visualize the distribution of these model terms, we present the uncertainty distributions of these terms. You can see that the distributions of some of these terms are very similar to normal distributions. For example, the fifth one, because they have relative lower HE values than the EX and EN values. But for some of the model terms, the distribution is far beyond the normal Gaussian distributions. For example, the fifth one, you can see that in the estimated parameters that the value of HE is similar or even larger than the value of EX and EN. So it makes it beyond the Gaussian distributions. As using the identity model shown in the previous slide, we can generate the prediction intervals. As shown in the left-hand figure, you can see that for each time point, we not only have the predict values, we have a predicted range of the PM 2.5. So some of these are narrow and some of those are large. It is because that in the normal times, the uncertainty is not that big, so that prediction intervals are narrow. But for the peak values, you can see that the uncertainty is strong, so the prediction intervals become wide. So that is how the prediction intervals can quantify the uncertainty predictions. We also present the uncertainty predictions in the right-hand figure. You can see that for each figure, each subfigure, it shows the prediction intervals of a certain time point. These time points are both from the peak value, so we can see that we have quite wide prediction intervals indicated by the red dashed line. You can also say that we have a average prediction of indicated by blue line. We have the observations indicated by the black line. You can say that all the true values are within our lower and upper bound, so that you can see that for this peak value prediction, this possible range of the predict PM2.5 can provide some reference, so that, for example, actions can be taken if the values may exceed the threshold, because you can see that in the first figure, you can see that it means that there is a risk that we have an error larger than 100. So some official institution or government take actions before this happened. We also present some statistics of the comparisons of our results with other methods. So we evaluate our model on 2 data sets to provide a robust result. The first, I would like to talk about the comparisons of average predictions, is named as APs. So our method is ICE algorithm. You can see that it outperforms all the other methods, including neural network and Gaussian process model. It also have similar performance as the traditional CCNE algorithm. It's because the new algorithms aims on improving the prediction intervals, but for average prediction, it has very similar results as the previous method. Now let's move on to the evaluation of prediction intervals. So you can see we compare with the traditional CCNE algorithms and the Gaussian processed models. You can see that first, you can see that with the similar PIA values, the proposed method has lower PIW, which means that the prediction intervals are narrower, which means that they are more accurate than the GPR model, which Gaussian process model. It also is the result is consistent and even better in the actual data set, Guangzhou data set. Now let's compare with traditional CCNE algorithms. The CCNE algorithms uses the same resample rate as the ICNE algorithms. But you can see that for the initial resample rate, it fails to produce a good prediction intervals. It has a very low values of accuracy. As we mentioned, it still need extra many manual steps to find good models using these traditional CCNE algorithms. So in summary, you can say that the proposed ICNE algorithms produce better accuracy, and it is also more efficient. A summary of today's work. So first, we use uncertainty model, Cloud-NARX models to quantify the uncertainty predictions using only 3 parameters, EX, EN, and HE. And we can also visualize the uncertainty using our distribution function. Second, we produce the proposed method produce fully interpretable models. You can see in the selected features, which we can clearly tell which of the factors can affect significantly on the PM2.5. And third, our proposed algorithms gives better result regarding the prediction interval accuracy and wise than some other models, for example, neural network and Gaussian process models. So that concludes this today's presentations, and please let me know if you have any questions. Thank you.
Okay, sorry, I have problem with my microphone. Okay, thank you very much, Yuanlin. Very nice presentation, very good work. Somebody have any question? Okay, I'm going to proceed with some questions. My first question is related to the following. You mainly attack the uncertainty problem with your model, but what could be the relation with the variability? How can there is any connection of this model with the variability, or are two different phenomena to attack?
Sorry, so you're asking about the application scenario, right? So how the model can be used on different scenario. So this model is initially proposed for the space weather predictions. And so this work is an extension of the Cloud-NARX model and to work on an improved version to estimate a model. This model have also been used to predict the EEG signal, which is a biomedical signal. So this is a 3 application scenario we have been working on. And due to the quite generic framework of this proposed method, I think this work is suitable for, well, I think most of the time series prediction tasks with the requirement for uncertainty analysis and also the model interpretability.
Okay, thanks. So one of the difficulties of the Gaussian process is to predict. It's very good for in the training part, but in the prediction part has some issue that maybe not the best model. So you said that this model has a very good performance in the prediction part, where you don't use this data to training the model. Is that correct?
Yeah, actually, I very agree with you because the Gaussian process model requires estimation of the Gaussian distributions and the prior parameters. But this one is our proposed models is based on a black box modeling system, so that even if we don't know what is the dynamics of the system, we can still apply the feature selection method to select and identify the most effective model terms from the input variables. So this actually can largely improve the prediction accuracy because we avoided the overfitting issues so that the model can be better interpret on the new data, new coming data. And also we reduce the number of the predictors in the models that makes the model more efficient that at describing the mean dynamics of the target system. So that makes the method better in predictions than some other models.
Okay, thank you very much.
Thank you.
Any further questions? We have space for one more. I'm reading you. Okay, so I have one more. I'm very curious in the part of interpretability. You said that it's fully interpretable. The model is very nice, but how do you read it by reading these parameters of the 3 parameters? You can how can you interpret this model? If you can explain a little bit more.
Yeah, thanks for the question. I think it's a very good question. So about regarding these 3 parameters, so actually the first parameters is EX. It is actually traditional parameters. It only uses EX. The model is actually turned to traditional regression polynomial models so that you can know the average values of each each identified model terms. So this kind of provides an interpretable model structure to provide prediction because we can clearly know what is the variables we are using, the predictors we're using, and their weights indicated by the first EX values. As for the other 2 parameters, which is EN and HE, they are used to describe the distributions of the weights. That is also the model parameter uncertainties. So they are used to produce the prediction intervals. From understanding the models, this can be used like a quantification of the weights. And for the result and visualization of predictions, it generates the prediction intervals, which actually is interpretable by humans because they are visualized, and you can clearly see the range of the predictions, and also an upper and lower boundary, as well as the probability of each range. So that's the interpretability of this model. Thank you.
Thanks. Thank you very much.